Hey folks, today I would like to talk a bit about what I have been up to for the last several months. The research I've tried to conduct, the lessons I've learned, and also some future plans regarding the game I'm currently working on. So basically, let me make some sketches here to explain what I'm talking about. The main point of focus was the gameplay, and the thing that I wanted to work on was the way you conduct your fights as a player, right? And we have this grid that represents the battlefield, right? And then we have our inventory, which is currently uh, holding playable characters. We have 4 slots in the beginning of the game, and then we drag and drop the units onto the battlefield. At the same time, the enemies are coming in waves from the right side of the screen, right? And currently, I only have a very simple enemy, the B character, and it kind of floats towards the player, right? And whenever the collider touches the playable characters, it starts inflicting damage. Now, the losing conditions are basically there is one losing condition, which is when any of the enemies, like in Plants vs Zombies, when any of the enemies reach the starting line, this line on the left side of the screen, and we have like the player carriage here, which hosts like our inventory and our main character of the game, etc., etc. So whenever the B or the like any enemy character reaches the starting line, it effectively means that we are in danger. So the carriage kind of disappears, and then we are being transported to the last bonfire where we've saved. Now that's kind of the main premise. Now I was thinking about how to make the combat fun to play, and I ended up with this idea that maybe you have several characters on the battlefield, and maybe it's fun to micromanage each of these characters, uh, and kind of dance on the battlefield. And this would mean that the enemies would appear in certain patterns. And the more you play the game, the better you kind of recognize the patterns, the enemy formations. And once you recognize the enemy formations, you might devise a strategy on how to be victorious against that particular formation. And as the number of enemy characters and the playable characters grow, and with the variety of different types of battlefields, the strategies you could have in the end could be numerous. So it could be fun, and it could allow for replayability, and it could also allow, I think, for different quests and different achievements the player could unlock. So the main issue here is that now we have kind of a real-time strategy where you control many characters at once. And we only have 10 fingers, right? We have one mouse, we have one keyboard. And now the complexity is in mapping our intentions onto the battlefield using basically what we can use, which is essentially 2 hands and 10 fingers. Now, one of the ways to implement this would be to have a sort of focus that would be assigned to one cell at a time. And the focus is what you are working with. You manage the position of the focus on the battlefield and then use that focus to move or to arrange your playable characters in a certain formation. It is to perform the dance. Now, when the battlefield is empty, you need to have some way of putting the characters on the screen. It could be done with the mouse, but it's a bit slow. So I'm thinking that there should be a system that would separate the battle into 2 phases. The first phase is your planning phase, is where you use your keyboard or your mouse to kind of plan and put your troops on the battlefield in a way you envision. And then the second, once you're done with setting up the formation of your troops, the second phase starts, and that's when the battle starts, and that's when the type of control you have over the battlefield is going to involve the moving of the troops in a very fast-paced fashion. So, first phase, you put your characters on the battlefield. Second phase, you use arrow keys to kind of let's say switch your focus between characters, and then maybe you use a modifier key like Control or Shift together in conjunction with the arrow keys to move the characters around. I'm going to illustrate my current work in progress implementation of this system. And it seems to be working more or less, but of course it would need some testing. Now this was one part of the task. Design control mechanisms. The second part was to design the actual patterns that would be fun to fight against. Design enemy formations. Now let me first illustrate let's see. Okay, let me illustrate what I'm talking about, and I will run the current version of the game. First, I need to let's say we start in the main menu, and then I start the game. And let's see how this works. So basically, this is a work in progress type of focus. Whenever we hover over a character, we get this this kind of ring around the character, which means that we are focusing on it. And then we can pick the characters, and we can also place them in different spots. And whenever we hover, again, we gain control of that character. Now, when it comes to the actual battlefield, let's go somewhere. We would end up in a fight. Now we have all of these characters in the inventory, and I am placing them on the battlefield. And now I'm going to use my mouse to control, my keyboard to control what's happening on the battlefield. Basically, the idea is that I gain focus of a character, then I use WASD keys to move the character around. And then if I use the shift key, the shift modifier, then for example, I can press shift and press A, which is to the left. The focus shifts to the left, and vice versa. And then I can use the WASD keys to kind of move the character around. So this is a work in progress type of implementation of the fast-paced navigation on the battlefield. Now, after this has been done, the question was, okay, how do I design the enemy formations? How do I make interesting combinations consistently? And that's when I started, that was the initial problem that kind of appeared seemingly out of nowhere, because turns out it's not straightforward to come up with interesting combinations. And so after I implemented, let's see where this is. After I've implemented like a rudimentary system to kind of describe how the enemy waves are happening, how they are appearing on the screen. Basically, we can see here every column is half a second, I believe, and a 1 is essentially an enemy, and 0 is an empty, essentially nothing. So we can see that we get 4 enemies on the first row, 3 enemies on the second row, and 3 enemies on the third row. And playing with this is fine. The problem is, after I decide, okay, this is my like first type of enemy formation. This is the first pattern. And then after I kind of jotted down, I have to load the game up and I have to test if it's actually fun to play. Does it have any interesting aha moments in how you approach the pattern, right? And this turns out to be kind of a complicated task, because I have to adjust the variable and then I have to play extensively. It means a lot of beta testing, essentially. So naturally, I thought maybe there is a faster way to kind of do this. And then I thought maybe I could use artificial intelligence to, like, not artificial intelligence per se, but maybe I could use neural networks to do the job for me. And then I started imagining how it could be useful to have a neural network that could basically playtest my levels, learn how to play the game every time I change the system up. Every time I introduce a new variable or a new enemy type, or I change the pattern, etc. And then it could have also been a way uh, to test the implementation. Am I getting soft locked somewhere? Are the levels playable after a certain change? Maybe like it becomes impossible at a certain stage to finish the game, etc., etc. So it's kind of like uh, a beta tester that knows the game much better than I do myself. So that's the initial idea, right? And that's what neural networks are for in the end. And so I don't have any background in artificial intelligence. I don't have any background in neural networks, so I had no idea what I was up against, and I decided to basically watch some tutorials and watch some courses. There is a lot of free stuff on the MIT's YouTube channel, and I made a whole list of different resources I wanted to go through. And let me see if I can get my my hands on it. Actually, let's see. Yes. So basically, this was the algorithm. I first looked at some basic maths and like the freshened up my memory of the derivatives and whatnot. Then I got some Python fundamentals in place because last time I wrote any Python was, I think, 3 or 4 years ago, which is a long time, and I don't use it like in my daily life. So I needed a bit of a refresher. And then there was several very very cool courses on YouTube. And I will link the channels probably in a GitHub gist, and I will add it to the description of the video so that it's easier for anyone who is interested and has no idea what this is all about, just like me. And then I looked up some deep learning stuff, and then finally I was able to look into reinforcement learning, which is essentially uh, the types of algorithms that could be used to train an agent based on the game and not on the static data. So to kind of summarize, uh, I wanted to have a neural network that, given the state of the game, could predict the best actions I could take in order to win as efficiently as possible. And that's the gist of it. Now, there are two main frameworks that people usually use. One is TensorFlow, and the other one is PyCharm. Is it PyTorch? I'm very sorry. The other one is called PyTorch. I had absolutely no experience with neither of these frameworks, and I had no idea what I was doing. So basically, with help from ChatGPT and a lot of tutorials, I managed to make some reinforcement learning models in TensorFlow and in PyTorch to see how they both work. A little bit of a spoiler, I didn't get exactly what I wanted to get, which is the neural network I have modeled and trained ended up being really dumb. And I will show some videos as well that I captured using those models. Now, basically, and this is partly to register what I've done so that me from the future can look at this video and get a refresher, or maybe see the mistakes I've made so that I could pick up from here and continue, because I'm going to have a pause in this whole machine learning area, because I'm not sure if the problem I'm trying to solve can be solvable in a reasonable amount of time. And I don't have enough experience. So I'm going to do it in a background. And this video is also going to serve me as a type of passive documentation. So basically, from what I've learned, a neural network, let's imagine, I want to kind of share my current understanding of how these things work and what neural networks are and how they operate. And to do that, we should imagine a simplest neural network, which has some input, has one single what's called a neuron, and it has an output, right? Now, this is the simplest you can get. And at the same time, I would like to look at an equation for a simple line, a linear equation, which is this. Now, if we try to plot this equation, we would get a line. And the B stands for basically how high up or down your line is. So it basically essentially moves it along the y-axis. And the M here is basically going to rotate the line. It's the angle, the slope. So this is an equation that could model any kind of line that you would want to draw. Now, there is a correlation here, because every neuron has a weight and a bias, right? And then we have a weight 1, and then we have a bias. So this is our simplest neural network, and it has a striking similarity to what the line equation looks like. And essentially, let's say we have some data. These are our data points, let's say, and we would like to find a line that approximates this cluster of data points, right? And we can start with a simple, like, arbitrary line, which means that the initial weights and initial biases would be initialized to a random number. So if our M and our B are random values, we would get a random line that does not fit into our data in any way. Now, the goal here is having the data set from real life. We want to fine-tune our neural network, which currently is extremely stupid, and it consists of only one neuron. We want to fine-tune it, and it has changed the weights and the biases, which is we only have one weight currently and one bias, one M and one B variable. We want to change the weights and the biases in such a way that would give us a line that closely resembles the data. And this is very useful if we want to give an arbitrary X value to an arbitrary input to our neural net and get a fairly reasonable Y value from it. And to do this, to find the values of the weights and the biases in our neural network, we would need to first get randomly initialized versions of these variables. So we get a random line. Next thing is, for every of these data points, we are going to measure the error, essentially what is also called a cost. So this is our deltas. This is the errors that we have. Then we would have something that is called a cost function. And there's a huge variety of different types of cost functions, and like each of those have a certain use case and a certain scenario. They are much better to use than the others. And the most common one is called the mean square error. And let's see if I can Google it. Mean squared error. And here we get this function. And essentially, what this does, let's see. One divided by n, and then we have a summation, and then so basically we have the difference, the squared difference between the y value and the y value that we predicted. So for example, the real data, the real world value for this is here, but our prediction is way off. It's here. So we take the difference here, and we square the difference, and then we do it basically for each one of the pairs of real world data points versus the predicted data point, and then we sum them up, which is what the sigma stands for. We start at the first one, and then this is essentially a for loop. We continue over every delta squared, and then we sum it up, and then we divide it by the number of our data points, and we get a certain number in the end, right? And if we are to plot this function, this is where it gets interesting. Now that we have this mean squared error function, our cost function, that kind of tells us how our predictions are different from reality. And if we are to plot, let's say this is M, this is B. And if we are to plot this graph, let's see. I'm going to do a very simple example. This is this is not reflective of reality in any way. Actually, let me find the screenshot for this, because it would be much better than me trying to draw it manually. Let's see. See if I can find it. Here's the perfect screenshot. Right, so we have our m and our b value, and if we are to plot our mean squared error function, let's say we get something like this, just for the purposes of illustration. And now, since we have a randomly initialized line, let's see. This is our randomly initialized line, right? Which means m and b, idest weight and bias, are some random values. Let's say we are like somewhere here, maybe. Let me pick a better color. So let's say we're somewhere here. We have two random values, right? And then the cost of this two values, of the weight and the bias, would be like, maybe, let's say in this graph, like maybe 750, right? And this means that our divergence from real world data is pretty big. What we want to do is we want to find such m and b values that our cost with our divergence from reality is at its minimal value. Ideally, it should be 0, of course. And if we find this point on this graph, we would find values of the weights and the biases of the currently single weight and the single bias for this neural network that would end up fitting the line equation into this data in this manner. It is the best fit for the data that we have at hand. And so our job is to find the m and b values, the weight and the bias, so that the cost is minimal. Now, there is an algorithm that could do it for us. And basically, we start at a random point in the beginning of the training, right? We start at a random point. Our job is to find this point right here. And to calculate it, we can use something that is called gradient descent. Gradient descent, like if this terrain of the function is a gradient, then we want to descend. We want to slowly go and find the minimum of this terrain, the local minimum. And basically, the good news are that all of these algorithms and functions, they are already implemented, and that's why people use TensorFlow and PyTorch and frameworks like that, libraries. So we don't need to implement these things on our own, which is very good because first of all, I would not consider myself anywhere near competent to do that kind of stuff. And second of all, even if I did, it would not be performant enough. So the performance would suck. And I, of course, don't want that. And I kind of don't care about the algorithms themselves. I only want the end result, which is, I think, fair to assume that most people do. So by using the gradient descent algorithm, we make steps towards the local minima. As soon as we find the local minima, we can say that, okay, our weights and biases are fine. Now, this is the general idea of how the neural networks work. Now, this is not enough, because after going through this stuff, I started thinking, okay, so this is how neural networks work, and this is fine and dandy, but I have a game, and I want to train it against the game. And that's where the reinforcement learning models come into play. There is a big variety of different reinforcement learning models. And let me see, I have... Can I do this? I made this, I found this chart somewhere on the internet. I have no idea where, but I copied it because I wanted to see how many algorithms are there and what can I do with them. Of course, this space is constantly changing because people and researchers keep on doing really good work and coming up with new ways of solving this algorithmic problems. But basically, it is like this graph covers, like, I would say, majority. And we have reinforcement learning algorithms that are useful for systems in which the number of states is limited, and then there is a different category for the unlimited. And then we also have the action spaces, whether we have discrete action spaces or we have continuous action spaces. Now, the difference is, let's say, and I am going to illustrate this as well in a video I have captured from the training session I've done earlier. Let's say we have a game in which we are driving a car, right? So we have the wheel and a steering wheel, and our controls are basically rotating the wheel left or right? And if we're using the analog wheel, this value would be a floating point value, right? So it would be like 0.15 to the right, or it would be 0.01 to the left, etc., every tick of the game. And this means that the action is not simply left or right. The action is a continuous variable. And in comparison, if we had a Tetris game, you know, where the blocks are kind of falling from the sky and stuff, then every action, what would be the actions in this game? We could have a right, left, downwards, which is going to accelerate it, and then we have rotate right and rotate left. Now this is a discrete action space, and in this example we have kind of a continuous action space, and based on these conditions, you would typically pick a certain algorithm. There are also other things that people consider typically, and this, for example, my game I'm currently working on is a browser-based game, and I am currently running it from a local server at localhost. It doesn't have any backend yet, right? It saves the state in the browser, in the local storage. And it's not very, it is possible to run multiple instances of this game because there is no it's not tied to the backend. It would not involve creating different separate backend accounts for every client, but it means that I would need to use something, I don't know, maybe like Puppeteer. I don't even know how to spell this. How is it spelled? Yeah, Puppeteer. Yeah, it was correct. Which is essentially like a library to control multiple instances of the browser. So I could use that to spawn multiple instances of the game, and then I would have to orchestrate that with the Python scripts that would train my models so they can go and interact with each of those clients. And for example, this kind of means that there would be certain restrictions on the way the algorithms work. And for example, for this particular use case, A3C, which is the actor critic algorithm, is used, and it can learn from multiple different instances, and then it can bring together all of that knowledge that it gathered through playing with different instances and update the weights and biases and update the model. Essentially, and an algorithm like DQN, for example, which is the deep Q network, it won't be able to do it out of the box. So you would have to make some adjustments. So yeah, there is a lot of different algorithms. I have tried to implement the DQN, and then I've tried all of the different flavors of DQN, which is double DQN, dueling DQN. I'm not sure what this stands for. I don't remember. This is, I think, is a double dueling DQN, and this I don't remember what these are. But essentially, and then there is also something like on top of this, which is like there is a certain amount of I think there is a bit more of different flavors of DQN, and then there is the thing called rainbow DQN, which is kind of the ultimate DQN algorithm, which combines a lot of different features, and then it's very tweakable, essentially. Yeah, so I have tried running the game and training it against the different variations of DQN, including the rainbow DQN, but after like 10 hours, I would still not get great results. And then I have also tried proximal policy optimization algorithm, which also did not turn out very nicely. And then I kind of got a bit disappointed because there is a lot of different algorithms. There is a lot of time that has to be spent in order to tweak them, tweak all the hyperparameters, and implement them, find working implementations and understand how they work, etc., etc. It is a very time-consuming process, and I don't have sufficient experience to do this efficiently. So that's the main reason, one of the main reasons I have decided to pull the plug and kind of have this session in which I go through the things I have tried and I failed at. Now that we have this stuff, we can take a look into how this works actually in real life. So, because the game was not intended, like I did not think about training and neural networks when I was starting to work on the project. And so I didn't have any instrumentation to allow this kind of communication with a Python scripts that would train the neural network inside. So I had to rework some things, redesign a bit of code, and essentially I ended up with splitting everything that happens inside of the game from the user's point of view into different actions. So I designed my actions that would make up the action space. And then I had to serialize the state of the game that would feature every variable that is important for the battle to happen. And this implies the positions, the health, the availability of all the characters, the setup, the position, the properties of the inventory, all the different enemies, their positions, all the different timestamps for the projectiles, etc., etc., etc. There was a lot of data, and each of these data points would have to be serialized into a huge array of numbers. Essentially every tick, kind of. So basically, I would end up with a state and I would end up with actions. On top of that, I needed a system that would allow me to pause the entire game and to play one tick. And one tick would not mean 1/6 of the 1/60th of the second. It would not mean one frame of the game, because that's a bit unnecessary. I wanted to have a meaningful tick in which something meaningful could happen for the neural network to kind of get that information and make something with it. So I have decided to, I think it's around, I don't know, but I think it's around like 20 frames or something. Every 20 frames or every second, I would issue a pause, and then I would analyze all of the data points I have from the state, and then I would consider how I would do the gradient descent. I would consider which action should be taken next, and then I would send that action back to the browser, back to the game. The action would get performed, the state changes, and a second later, I get the new state, etc. And the loop continues. And also, to implement that, I needed a pause functionality, which is something that we can see now. I'm essentially, like, for debugging purposes, I can press space and it pauses the game, and we can see it. Oh no, I forgot the characters on the battlefield. Not good. And let's go somewhere. Okay, so now the game starts and then I pause. Then I would send the action. The action is implemented, performed, and then the game would commence for some amount of time, and then I would get a pause and I would get the new state. Now, I of course don't want this stuff to be present in the quote-unquote normal game code, right? So I had a separate scene I've set up to kind of play around with this stuff. And let us run the game in that mode. Let's see. So I would like to start, where is this? Not from the main menu, but I would like to start the playground. And let's see what the playground looks like. Oh, I need to start. Okay. Okay, so this is the playground. And the communication between the backend and the frontend is done through WebSockets. So essentially, the Python script would create a WebSocket server, and then the browser is going to connect, is going to try to connect. And since there is currently no backend running, it keeps on trying to connect to the backend. Now, let's see the current implementation of the proximal policy optimization algorithm, which I shamelessly copied from a tutorial. And let's see. This is using PyTorch. And here I'm creating a server. I'm creating my agent, setting up all the hyperparameters and stuff. And then for a certain number of games, let's say it's 300 different games, I am waiting for the WebSocket message, and then I get the state, I get the reward, I get the flag, whether the game has been won or lost, so that I could proceed on to the next game, etc., etc. Now, this is probably a good point to kind of talk a little bit about how reinforcement learning works in general. So just like we discussed previously, we have some data, and then we perform gradient descent over our cost function, which is we have a prediction and we have real data that we can work against. Now, when it comes to reinforcement learning, we have our game. We give the game a certain action based on the state that we have. So we have the state, we look at the state, we say, okay, given this state, this is the action you should take. And then we send the action to the game. The game internally implements this action, and then it spits out new state, but it also spits out the reward, which is every time you make an action, let's say you lost the round. Okay, we can set a reward to -100. You killed an enemy. The reward could be, okay, killing an enemy is good probably. So we give you a reward of 10. You won the round. That's great. We give you a reward of 100. So reward is just an abstract notion that tells the neural network how well you are doing. So we return the state, we return the reward, and we return whether the game is done or not. Should we continue playing it, or should we start a new game instead? So, and this is just a bool flag. So, just a true or false value. Now, reward in this particular scenario, reward is kind of the opposite of the cost function, because we want to minimize the cost function, but we want to maximize the reward. So this kind of paradigm fits nicely into classical neural network concept, because we have some data and we know more or less how we want to we know more or less how we want to change, in which direction we want to change the data, because we have the reward, which is if we did something and it's bad, then we try to not do whatever it is that we did. right? And then we try to understand what was wrong in what we did, etc., etc. So we have the reward, and then we get the state, and we get the reward, and we get the done every time the browser talks to our Python server. Now, when that happens, we evaluate all the information we got from the browser, and then we learn from it. And then we send the message back. We say, okay, browser, now this is your action, right? We send back an action via WebSockets, and then we say, this is the action that we chose based on the information that we have in the neural network. And then it sends the action back. Now here, the browser is listening. Once it gets the action, it acts on it. For example, if it's shift focus to the left or to the right, or move the character to the left or to the right, and then it does the calculation of the game logic. And then a certain amount of time later, let's say a second later, it sends the message back to the Python server. And so the process continues. Now, to orchestrate this, I've added a simple agent class that has some actions. So we have currently, it's a very simple version of the game. It's the actions you can take is nothing. You can move up, move down, move left, and move right. And then essentially, let's see. Let me log the state, and I can also log the reward, probably. Let's see how this works. But before I do that, I of course need to start the Python server. So we're going to start the script, and then let's refresh. And so now we can see the neural network playing the game. And it kind of does very badly because it has not been trained for a long time. And also I suck at modeling neural networks. So that's why it's stupid. Now we can see every time the action is taken, we can see the action here, and we can also see the state. Now we can see all of these different variables, and we can actually look up what these variables mean. Because whenever the agent class is serializing the state, we can actually see it here. So first, we get the number of player units, number of enemy units, number of projectiles currently in the frame. And then we get all the information, like individual player units data points. And this would include the position, the XY position, the health. And then it would include, dude, I don't even remember what this 0 stands for. Again, this is not production quality code. This is just work in progress type of code. So it sucks. We have, this is the enemies. Wait, I want to actually look at the player units. We have health, we have the attack timer, because every once in a while it would create a projectile, and I decided, you know what, maybe the neural network would benefit from knowing when exactly the projectile has been released. So each of the characters would have its own timer that increments up until the next projectile is thrown, then it resets and then continues on incrementing again. So this is kind of like a looping timer. And then I don't remember what the 0 stands for, I would be honest with you. And then we have whether it's dead or not. I don't remember why these are branched here as well. There is a reason for it. And then whether it's selected or not, whether we are focused on it or not focused, because that is also extremely important if we have many characters. So essentially, this is the data, and then the next step, usually what neural networks like, is data normalization, because this is all a numbers game, and numbers are very important in the shape of the numbers that we get is also very important. So for example, numbers like 0, 0, 0, and then 1001, 1002, it's kind of not nice because they're all over the place. Having a 1000 next to a 0 means or next to 1 means 1 is practically like equal to 0, and then the difference between these two numbers is much greater, and then it could introduce unexpected behaviors, essentially. So what usually people do is normalize all the numbers on the scale from 0 to 1, or -1 to 1, like this. So they're all kind of homogeneous in the way they are spread. So we won't have, like 10 billion and 1 somewhere, and then like 100 billion, etc., etc. There is like just too much of a range. We want to keep the range normalized. And then the same thing would go for I'm actually not sure, because in some places I've read that, yeah, essentially the normalized rewards, for example, if we have -100 and then 100 and then 1000, which is like unnormalized rewards, like in some places I've read that, it doesn't matter. In some places I've read that it could make a difference, but I'm not sure, so I won't speak much about this. Yeah, so basically here the normalization happens, and essentially what you get is every time, see if I'm outputting, yeah, so basically for every game we end up getting a score, which is a total reward, which is like -200, it's a bad reward. -400, even worse, right? -250, a bit better, but still like crappy. And then we get average score, and we get the time steps that we played, and learning steps that we have taken, how many times we learned through the episode, through one playthrough. Now this stuff is, of course, it's also running on the GPU, because you want to run this stuff on the GPU because CPU is way too slow. So you have to make sure that your setup of TensorFlow or PyTorch is running against your like 1490 or something, right? Because otherwise it's very slow, and it also takes a lot of time. Now, one of the issues that I've encountered is, aside from picking the right algorithm, aside from picking the right data, and aside from picking the right set of actions, you would have to fine-tune your neural network to make sure it does what you want it to do. And that's a very tricky process. It is essentially, you are in the, like, maybe it's just me, but I felt like I was in a dark cave and I was trying to go in some direction, and I don't know where I'm going. I don't know how far I should go. And I just kept tweaking different variables. I kept tweaking the algorithms, and then I kept waiting for hours for the training to complete. And then things like TensorBoard, which is basically all of these values, you can actually plot out. and you can look at them, like using a tool like TensorBoard. Let's see. So basically, you have a bunch of these charts, and then you see how your cost value, for example, changes, how your learning rate changes, what your weights and biases look like, etc., etc. And then based on this, like, you run it for several hours, you look at this stuff, and then you try to think, okay, what is the problem here? And of course, the more complicated the game, the more complicated the data, the more complicated the tuning of the parameters is, unfortunately. And so I got to a point where I could get some of the interesting behaviors emerge. And as an example, I can show this clip that I recorded, in which the neural network figured out a way to basically not get the penalty of loss. And there is a quirk here, because something that I haven't implemented is whenever you are moving the character around the battlefield, you're actually despawning it and then spawning it back in, which kind of implies that the health goes back to 100%, right? And so if you keep on moving the character around, it would kind of become immortal. So the neural network figured it out. And so that's precisely what it is doing here. It just keeps on moving up and down, up and down, up and down, etc., 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 just to not get the penalty. So that was kind of like an interesting, intelligent behavior that was not designed. However, I could not get it to work consistently. And one of the issues here is that the rewards that you would set, like, it's a very fine line, because if you set your rewards so that it wins against a certain game, you can absolutely do it. You can absolutely make a reward for every action in every state space. And then your rewards would be extremely fine-grained, fine-tuned, but then that means that there's going to be no intelligent design in the neural network itself, because your rewards are kind of biasing it towards doing what you want it to do. So you can't have too many different rewards. You can't say, for example, that if you're alive, that's good, if you're dead, that's bad. Because there could be a strategy that would involve killing off, like doing a gambit, killing off your characters in order to gain an upper ground, right? So you can't code those type of behaviors if you want to explore the game design landscape. And that is the main goal here, was to see what the game is capable of. How can I inventively play the given set of enemy formations, right? What can I do with it? What's the outside of the box thinking? And to do the outside of the box thinking, the only real thing that matters is whether you lost or not. That's kind of like the end game. And but this unfortunately also means that you have very little rewards, and it takes much more effort and much more time for the neural network to train and to understand what is the best strategy, because it is much more complicated to design a model that would look for a strategic action to take and not a tactical one. Because strategy would imply knowing what happened like 5 minutes in the past, right? Or whenever you take an action, even though reward is abysmal, you still take the action because you know that this thing could potentially end up in a very good state later on, right? So that is the intelligence that helps with the outside of the box thinking, with the design process. But it is extremely difficult. It is extremely tricky. And there is a lot of different things people use. Like, for example, there was this, I think, was it the Dota? Yeah, it was Open AI and it was Dota. And basically they trained a neural network to outcompete human players. And there is a lot of things that went into there. It's not something you can do over one weekend. There is a lot of different tricks. They, if I'm not mistaken, they also used pre-trained data, which means that they're also like, it was in some sense supervised. But supervision is not a simple thing to implement, because like imagine you have some behavior that you have in your neural network. You don't know where the behavior is, because it's a combination of the weights and the biases and your layers and everything else that is encoding it and holding that behavior. So when you try to when you try to use pre-trained data for something, it is not a very trivial process. And then there were months and months of training to actually achieve the strategical thinking, and it was not done on one GPU. So given all of those things, it is not currently extremely clear to me whether I can train something more complicated than the simplest example. And this is, for example, it's what's called OpenAI Gym environment. So it's a set of free games, so to speak, you can test your algorithms against. And in this case, I think this is the proximal policy optimization algorithm that runs against the inverted double pendulum example. And as we can see, like this is a recording I've done on the example I've trained for, I think, 2 hours on my 4070 GPU. And essentially, it kind of learned to balance it, right? But then we have to also remind ourselves that it's just a couple of variables. And there is really no strategy in mind. It's basically immediate actions you take on the immediate state you have. So this is a much simpler task than figuring out a strategy for a complicated game environment. So the simpler things, like they're fine. Like you can run them, and then you can make sure that your spaceship doesn't crash and stuff within an hour or so. But as soon as you start moving towards more complicated, as soon as I start moving to more complicated examples, I start to notice that my experience is insufficient. And so I had a hard time figuring out whether it's something that is doable for me, or am I going to waste a year of my life obsessing over it and trying to make it work. And so I decided to pull the plug on this one for now, until I get someone who could direct me in the right direction, or until I get more knowledgeable. So that is the current state. Now, with all this being said, the next thing for me is to return to the pattern design. Now that I have main battle mechanics and I have like a couple of enemy patterns, now the idea is to start adding variety. And I think I should implement another enemy type and then play around and see how that feels and looks like. And I need to discover as many hidden mechanics, emergent gameplay situations, as many of them as I can. And then that is the game design problem. That is what I would like to start solving next. And then hopefully I can get up something, get something that is fun up and running, and that would be great. So this is all for today. I think it was a long video, and yeah, I'll see you folks next time. Thank you for watching, and thank you to everyone who was watching on YouTube. I will try to make the next episode of this in a week or two once I have something to show you guys. So thank you again, and see you next time.